prove a formula of derivative of ax that is equal with ln a times ax. So prove formula for derivative of ax that is equal with ln a times ax. Prove. Recall the definition of the derivatives. The definition of derivatives states derivative of f of x is equal with a x in exponent x plus h minus a in exponent x divided by h. That is equal with the limit h goes to 0 time a in exponent h minus 1 divided by h time a in x. But how we came here? Here we came this way. Just let me give a small explanation here. For example, when we have this formula with this definition here, this definition f prime of x, we can write in this way: f prime of x can be equal with ax. Now I'm expanding those exponential time a in h minus a in x, which is divided by h. And as we see here, we have a in x here, we have a in x here and a in x here. So they factorized a in x, which is a in x here, and inside remains ah minus 1 divided by h, what we have here now. And now this part, limit h goes to 0, ah minus 1 over divided by h, we substituted by k. So we substitute by k. And let's see what we are going to get. And since we are substituting, the derivative of f of x is going to be k times a in exponent x. And now here we are in this formula what we had a little bit here. Ah we are going to substitute by et. So we are substituting by et. And now this here we are going to see, for example, if we are going both sides by the ln, what we get here, we get a ln that is in a in exponent h is equal with a ln e. Just let me erase this. Just let me erase this here a little bit. So is a ln e in exponent t. And now, according to the derivatives property, this h gets in the front here, what is here, and becomes ln a, and t gets in the front of a ln, what got here, t ln e. But this ln e, we already know just this ln e is equal with 1. Here. And 1 times t is a t, and h is h times ln a. And this here we divide by ln a, and finally we get the formula. We get the equation that is h equal with t divided by ln a. And now whenever we have in this formula here h, we are going to substitute with t divided by ln a, and whenever we have a h, we'll substitute by t. And finally, that expression k is going to be limit of a t that goes to 0 in exponent t minus 1 over, because this is a h, so we are substituting by h, and this ah is equal with at, and h is equal to t over ln a, what we already did a little bit early. And this expression here now, we have this expression e in a t minus 1 is divided by t ln a, t over ln a, this t ln a over ln a, what we can write this expression like et e in exponent t minus 1 divided by everything of this, this expression divides by t over ln a. T over ln a. And when we are doing some algebra here, everything here gets e in exponent t minus 1 is going to get divided by t times ln a. So that's how we get in this form. In this form here, what we got. But this ln a goes in the front of ln a is a numerical value, is a constant. So this gets in the front, and limit t goes to 0. We have this expression here, this expression, et minus 1 over t. And what we get here, now we are taking just this expression here, and we want to find the limit. So the limit is t goes to 0, and we have a e in exponent t minus 1 divided by t. But we already see here, if we are substituting t by 0, e in 0 is 1, minus 1 is 0, and here is t is 0, is indeterminate form, 0 divided by 0. So we use the L'Hopital rule, and according to the L'Hopital rule, the limit of t goes to 0, we get this form. We get a e in t divided by 1, and if we are substituting e in t is 1, e in 0, I'm sorry, is 1, and 1 divided by 1, everything is equal with 1. So, and because this is equal with 1 now, all this expression is equal with 1. Now 1 times ln a is ln a, so k is equal with ln a. And now we already saw a little bit earlier, this formula was k times ax, and ax we already did this k times ax. So what we have here, ln a times ax. So the derivative f of x is k times ax, but the k is ln a, and so finally we proved, is completed the proof, the derivative of f of x is equal to ln a times ax.